All right, I'll make the sign chart now and do the first derivative test. We know from what we said earlier that the radius of the cylinder is trapped between being non-existent at 0 and being the radius of the cone because it's trapped inside the cone. It cannot have a radius larger than the cone. So in reality, this sign chart is truncated on both sides this time. It is bounded below by 0 and is bounded above by the radius of the cone. All right, now I don't need to really put this critical value on here. It's on here already in a sense, and we know that this does not make the volume maximal because when the radius of the cylinder is 0, as I discussed previously in this problem, you're going to have a volume of 0. Right? Again, this corresponds to one of the extremes for the cylinder structure within the cone. Now really over here is the other extreme. If the radius became the same as the radius of the cone, again you have a 0 volume. So this is 0 volume for cylinder, and this is 0 volume for cylinder. And somewhere right about here you might say 2/3, turns out, 2/3 of the cone's radius is a critical value for the volume of the cylinder. So all we need to do is show that the volume of the cylinder is maximal here. This is what we anticipate. So if we take a test case between 0 and 2/3 R, like maybe 1/3 R, I don't know, something like that, you can easily show in here, if you picked a 1/3 R, 1/3 cap R, just think about it for a second, 1/3 cap R, i.e. R on 3, these would cancel exactly. You'd have 2 minus 1 is positive. Right? If this is 1/3 R, it's also positive. So the whole thing's positive, right? All these measurements are positive, pi is a positive value. The whole thing would be positive if I were to pick a test case of 1/3 R. I know it looks a little strange to take this very abstract test case, but because the problem itself is abstract, sometimes you have to do that. So R on 3. Doing that, we see that the first derivative is positive. If we pass 2/3 R, this is where it's a little trickier to get a good test case. But let's just imagine, without taking a particular test case, because it's a little confusing, right? What am I going to test in here? So 2/3 R to R. Let's just imagine R itself in here, right? If you put R in here, you're going to get 2 minus 3, because the cap R's are going to cancel. Right? And R out here will, of course, be positive. So these are all positive. But 2 minus the 3 value, if you picked cap R for the radius of the cylinder, then you would get a -3 value here. 2 minus 3 is -1. The overall value would be negative. So now let's just imagine you back up the smallest, tiniest amount from R, the smallest amount you can possibly imagine. Is it really going to change the negativity of this factor? Of course not. It's not going to change it at all. Right? So therefore we can say this must be negative. Now another way to look at it is what I've mentioned before, and that is this factor is to the first power. So since this factor is the first power, and really so is this one, it means it has to be an alternating sign chart anyway. Okay? That's another very efficient way to look at these things without having to pick particular test cases for these strange kinds of values here. It gets very confusing. All right, so now we know this is a relative max, 2/3 R. 2/3 R is location of a relative max, but not just relative, because on this closed interval, right, this is also an absolute max because you're going up, right? The whole time here, you're going up towards this location, and then right after you're going down, and you continue to go down even until R itself. So therefore, this must be an absolute max on that interval. So 2/3 R is location of absolute max for the volume function. So we now know what the dimension of the cylinder radius should be. It should always be 2/3 of whatever the radius of the cone is. As long as the radius of the cylinder is 2/3 radius of the cone, then for sure the cylinder will be of maximal volume within the cone. But they didn't ask us, here's the trick of it now. In this one, they did not ask us what the dimensions were. They said find the largest volume. All right, so now we just got to plug this value. All right, we know that RC equals 2/3 R yields max volume for cylinder. So all we have to do now is plug it back in to the volume function. So V, it's going to look a little confusing at first perhaps, but V of 2/3 R. I plug 2/3 R back in to V. So where was it? Looks like it's right here, right? This is where it's all in terms of RC. So each of these RCs here, all right, or right here really, either one, doesn't matter. We're going to change into 2/3 cap R. Let's just do this one. We'll have pi h times 2/3 cap R quantity squared minus 1 on R 2/3 of R quantity cubed. And maybe I'll use a bracket again here. All right, so we just need to calculate that. First thing we do is take out R squared. Or if you think about it for a brief moment, right? R cubed on R would be R squared, and this has an R squared. So let's take out the R squared. So we'll have pi h R squared, and now we need to calculate what's on the inside. So we would have 4/9, right? 2/3 squared. It's true you can also take out 2/3 squared, I understand, but I'm not sure that'd be obvious to most. So let's just do it this way. So we have 2/3 squared minus, the r's have canceled and are removed, so we have a 2/3 cubed here. So we'll have pi h, capital R squared. Remember, this R squared is a constant. It is the radius of the cone. And now I just need to take 4/9 minus 8/27. So 4/9 minus 8/27. If I just give this a 3 on 3, we'd have 12 minus 8 on 27. All right. So 12 minus 8 is 4, so we'll have 4/27. 4/27 pi h R squared. That's our volume. And that's the answer to the problem.